Dr. Moujaes is our own graduate. He received his BE degree and master's degree in mechanical engineering from AUB in 1972 and 75 respectively. And he earned his Ph.D. degree in mechanical engineering from the University of Pittsburgh in 1980. And his area of expertise is thermal sciences. He is currently a professor of mechanical engineering at the University of Nevada at Las Vegas. He has also 7 years of industrial experience in the US and Lebanon in the area of R&D in alternative energy and HVAC applications. He has almost 100 publications in refereed journals and conferences. He is also an associate editor of the Journal of Energy Engineering. In the last 5 years, he received over $1.3 million in funded research to work on high temperature hydrogen production, indoor environmental quality issues, energy conservation related to air duct leakage in HVAC air delivery systems. He has acted as a consultant to many regional and national companies on issues related to energy conservation, and he has been invited to be an expert witness on several legal cases in the Las Vegas area, I assume related to energy, not any other legal issues. Yesterday somebody said, is he on forensic issues? So I said, no, it is related to his expertise. It doesn't have to be only a criminal issue. Dr. Moujaes has helped graduate over 35 graduate students and established 3 student branch chapters at the University in Las Vegas, namely SMAE, ASHRI, and ANS. And he also established the SME professional chapter in Southern Nevada and was its chair for over 5 years. His talk this afternoon is entitled A Survey of Alternative Energy Sources and Conservation Approaches. So I should add that we are doing lots of work in energy-related problems here. In the faculty, we have a graduate program in energy, and with the addition of the chemical engineering, and we have also an Institute of Energy and Natural Resources, which is funding will fund 5 projects in the area of energy and natural resources. In fact, it is funding, and tomorrow morning there is a workshop on the topics. So this is very timely talk, and it is really a topic that is a global problem, a global challenge that many places around the world they are looking at this problem. It's not just local. Of course, Lebanon, the problem of energy has been going on for many, many years, and you can see that from the electricity every day. It goes on and off. So that's energy related. So please join me in welcoming our distinguished alumnus, Samir Moujaes.
Hi, everybody. It gives me great pleasure to be in this hall again. Since I was a student many, many years ago, I'm not going to tell you exactly when, so you don't know exactly my age. So I remember with fondness the activities we used to have here and all the chanting and singing that we had to do for the alma mater songs and all that stuff. So I'm very pleased to be here. I'd like to thank Dr. Haj and the selecting committee for their efforts. And this is just basically, as the title indicates, it is a survey of energy production and energy conservation topics. This is not meant to delve into any great depth in any of the areas, but just to hopefully pique the interest, since this is a student conference, to pique the interest of students in some of these topics, and then maybe they can pick it up and run with it, so to speak. So I hope it will achieve part of its intent. Some of the areas that I will touch on, again, it's not going to be in any great depth or anything. Solar thermal power generation, as I'm sure is very well known by now. Photovoltaic PVs is getting to be big. Of course, the cost of photovoltaic is still a bit high. So, until there is another probably breakthrough on the production of these photovoltaic cells, I think you will see probably a jump of their usage. Wind energy power generation is again big in certain areas. And by the way, I mentioned those. They are not necessarily tailored to applications in our area or anything. They could be not very good for our area, but these are in general what we see in the US and other countries. So don't take this that I'm suggesting all these for our area as a possible usage. Something that has come new is the use of municipal solid waste and waste water sludge to generate biofuels. This is a big area getting underway in Las Vegas. We have a humongous amount due to the presence of casinos and other waste generators, let's say, where you basically produce about 10 to 14,000 tons of waste, of mainly cellulose waste. And people are starting to think how we can use these before we dump them in the landfill. There is a great potential for using those to generate some energy as well. And I'll show you just a quick schematic of how we are suggesting to do that. High temperature hydrogen production. This is something I was involved in. Again, the idea is basically simply splitting water, but splitting water at high temperatures. It is a little bit more efficient than doing your low temperature electrolysis and things like that. In this case, what we were proposing here is to use solar energy as a source of heat, which then would be conducted to some of the reactions that could be used to generate eventually hydrogen. These reactions take place usually around 750 to 850 degrees Fahrenheit. So it's a fairly high temperature application. The last item that I will just touch on is the high temperature hydrogen production using nuclear energy. Again, it's a similar concept in a way, but instead of using solar energy as the source of heat for some of these endothermic reactions, we use nuclear energy in an indirect way, of course, to drive some of the high temperature hydrogen reactions to split water and get hydrogen from it. And this has been seeing some interest lately from DOE, who is basically the main source of funding for a lot of these projects and concepts. On the other side, I'm going to talk just a little bit about energy conserving technologies, which is the other side of the equation. It's good to try to produce more energy and come up with creative ways to do it. But on the other side, as consumers, we have to be cognizant of the fact that without energy conservation and being more efficient in using energy, you are not going to capture the maximum effect that you would like. And so energy conservation is probably as important as energy production. And it's been seeing a lot of interest lately from the Obama administration, as opposed to the Bush administration before it, which was basically claiming go and dig and look for oil. Again, the reason for both of these things is, as you know, I don't have to tell you, is energy is getting more costly to produce. Needless to say, the environmental impact of producing energy from the basically the major accident that we just had in the Gulf of Mexico kind of emphasizes the fact that we need to do this in a more socially responsible way. As far as I know from the news, this oil is still gushing out from the Gulf at a significant rate as far as the number of barrels, and it's going to probably cost a whole bundle of money to try to correct that. I've seen a documentary recently, before I came to Lebanon, that they have not basically finalized the cleanup yet of the Exxon Valdez problem that we have had, as you all know, in 1989. Its environmental effects are still being felt in that area. So some of the areas that I'm going to just touch on is what is called the zero or near zero energy homes, radiant barrier systems, radiant paints, thermal recovery wheels. Some of these are just ways of recovering energy, like the thermal recovery wheels in air conditioning systems. Innovative high thermal mass engineered wall systems, innovative high SEER HVAC systems. One of them is a product or a system called the FREUS. It's an evaporative cooled system which has a very high SEER rating and has been coming online fairly recently. The other ones that I will just touch on again are efficient lighting systems using LEDs, solar energy for heating and cooling. Again, this is not something new in general, but some of the applications tend to be still in the research stage. Geothermal heating and cooling, and from a more applied way on the residential side, envelope leakage reduction to minimize heat loss and gain. And something that I've worked on recently is the duct leakage reduction to minimize heat loss or gain. Again, as you probably know, HVAC systems in the US, mainly in residential applications, are somewhat different than what the trend has been here, in the sense that you basically use a split system here for each room or each couple of rooms because you have concrete buildings and it's kind of difficult to run duct systems in a very unobstructed way. In the US, it's somewhat different. They basically run the ducting in the attic and then they drop the registers from the ceiling most of the time. So depending on the installation effectiveness, you could have a very shoddy work that is being produced, and if you lose 20% of your supply air to the outside of the conditioned space, you basically have reduced your thermal efficiency of that system by about 20%. So it is a major problem and needs to be looked at into how to minimize these issues. As I wanted to qualify some of these applications, I just say a generic sentence here. Of course, some of these technologies may or may not be applicable to a certain locality, depending on the weather conditions and the type of construction used. In other words, low versus high-rise buildings, flat roofs versus an attic ceiling combination, and so on and so forth. So in other words, some of these applications may not be applicable at all in the Lebanon or the Middle East in general, and I have to qualify their applications thereof. Again, as I said, it is a survey, so it's going to be more image-driven than a lot of equations and analytical analysis here, because I don't want to lose the effect and of it. So these are basically some of the plants that have existed recently in the US. Some of you may be very familiar with these. It's a solar thermal power generation plant using parabolic dish concentrators. You have basically pipes that run at the focal point of these mirrors that reflect, of course, the rays onto that focal point. The axis of these parabolic mirrors only move in one plane. They do not swivel or anything like that. The size of this plant, it has been sized at around 380 megawatt of installed power. So this is not a toy, this is a real plant. It's not as big as a regular fossil fuel plant, but it's getting there. So this is one of the applications for solar thermal. Again, this just shows in a nutshell the arrangement of all the components. You do have a cooling tower, turbines to run the power generation, and these are the solar collectors up on top. And so of course, the efficiencies of these, I think by and large, the solar thermal have proven to be, in general, more efficient than your PV applications and a little bit less costly than PV applications. So probably, unless there is a major jump in or reduction in cost in PVs, these probably will see the day of light in their applications before the PV. I could stand corrected if something else happens, but that's some of the stuff that could be. This is basically, again, you've seen those a lot on a lot of probably roofs or whatever, photovoltaic power generation. This is actually, I pulled that from the web. It's an application in India, and it's a small installation, but just it shows the application. It's about 36 kilowatts of installed power in this particular case. Of course, we have much larger power installations in the city close to Vegas called Boulder City. We're starting to see some major installations coming to being. A lot of foreign companies, especially from Spain, who is becoming a leader in that area, are coming to install some large scale installations. One reason for that is because Boulder City and its municipality are very forward thinkers. They will give you the land for free or practically nothing, and they would let you install these. Of course, there will be benefits derived afterwards from some taxes and all that, and hopefully generating some of the jobs for the area. So again, one of the topics I mentioned, of course, before is wind energy power generation. This is in the Tehachapi wind turbine farm, which is on the route from, if you go on from Las Vegas towards San Francisco, I believe on Route 5, if I'm not mistaken, you will see those. There's about 5,000 of them installed, and again, they have to obviously be located in certain areas. After determining that the area is suitable for wind energy, there should be some initial studies, measurements, and they usually rate them by numbers. So a number rating for a good area, I think, should be between 4 and 5, which I think gives you an indication about the speed of the wind over a period of time. You cannot apply them or put them anywhere just because you think wind energy is good for you. It has to have the right qualifications for it. This gives you can produce 800 kW hours and provides power to, and for this installation, it says to 350,000 residents in California in that area. So it's not a small installation either. I don't know if we do have any installations here, just at least for testing purposes. Anybody know that in Lebanon, just to study the feasibility, or have any wind studies been done to qualify? I remember my, I'm sorry, they're producing some data on that? Okay, great. This is basically the other area that we would like to work in. We're still trying to get funding. As you know, there is an economic downturn in the US at this point, and trying to get funds is a little bit more competitive, as if it hasn't been before. This is the use of municipal solid waste and sludge solids to generate biofuels. There is a series of sort of mechanical, thermal, and chemical processes that need to be used to derive some of these biodiesel fuels. And again, the source for it, as I said, in Las Vegas, because of the existence of so many casinos, that we use the sludge from the wastewater treatment plant, and of course the solid waste comes from just refuse from the cellulose that comes out from all the casinos. As I said, there is about 8,400 from the solid waste and about 4,000 from the municipal sludge waste. So combined, you're talking about 12 to 13,000 tons a day, which is not a shabby number to use to get started on this. I think our friend from chemical engineering would probably be very interested. I've talked to him a little bit about that, and you may be doing some stuff here in it. This is an application that we've started working on in conjunction with Sandia National Labs, and this is basically the use of solar energy to generate hydrogen at high temperature. And the idea was to drop particulates here, very dark particulates of the order of about 700 microns vertically down, and focus on them, and you don't see those in there, but there is a series of mirrors that focus the solar energy onto an aperture, and the aperture basically, as the sun goes in there, it heats up those particles to a relatively high temperature, and then the particles are conducted to another place where they can exchange their heat with a reaction, a chemical reaction that would be one of 3 or 4 reactions to produce hydrogen at high temperature. This is, of course, still in the study phase, and Sandia has already built not a full scale, of course, but a scale that can be validated to a certain extent. They do have a facility at New Mexico which has about 200 mirrors that can focus their heat onto a relatively small area. And so this is one of the things that we looked at. My involvement in that was basically to build a small prototype of this to study a few effects. First, the solid fraction that is generated as these particles fall, because as we all know, the particles will accelerate as they fall down. So we wanted to find the opacity of the particles. If there is too much opacity or too little opacity, it can affect the amount of heat that gets gathered there. And so this is basically some of the plots that we have shown with position and with the density of the particles as they come down. And we also had another factor that we had to take care of, is the wind, because this will be open to the atmosphere. We studied the effect of wind, and as it blows onto these, what does it create? What kind of flow patterns does it create on the sand? And would it make it spill out from the collecting tank, and so on and so forth? So there are a few technical problems that have to be looked at before really we can say that this has a chance to be progressed to the next prototype stage. But these are some of the technical results. This is just a few images that show the opacity, or the density, if you will, of the particles at 0.3 meters away from the outlet here, and this is 1.5, 2.7, and then it's the same thing for a different density. So basically you can see that to a certain extent, as the particles move away from the inlet point, their void fraction tends to decrease and became more sort of, the visibility in them becomes more, because the particles are getting away from each other due to their acceleration. This is the other portion, the other application, which is the trying to generate hydrogen at high temperature using nuclear energy. The proposal here was basically we will have an indirect heat exchanger that will use, this would be the high temperature side of it. It's a compact heat exchanger with a very high surface area to volume ratio, something in the order of above 200 meters or 200 meters to the inverse, basically. So the surface area is fairly high, and this is the low temperature side of this. The idea was to suggest using a fluid such as pressurized helium on one side, and the other side would use a molten salt. It's called Fleniac, and this Fleniac has very good properties from a thermal point of view, in the sense it stays liquid up to about 13 or 1400 degrees C, but one of its drawbacks is it is highly corrosive, so we could not use alloys of metals in there. It has to use something like silicon carbide applications to do that. What we did in the lab was basically use dynamic similitude to try to obtain other fluids that will give us similar properties from the non-dimensional groups like Reynolds number and Prandtl number, so that we can start our analysis first at low temperatures before we move and start with something serious like using a FLENIAC at very high temperatures. And so this one, again, we worked with some of the people in Berkeley that have done some work initially on that, but we built our own test sections at UNLV. Again, these projects are all funded by DOE regarding to hydrogen. These are just some images to show you some of the stuff that we built. We used our CNC machine to develop some of these heat exchangers that are scaled, of course. These are off-center peaked fins that are staggered to try to increase a little bit the mixing. We've tested two types of fins, one with a rectangular edge to it and one with a rounded edge to it, to see what are the effects on there. And this is our generic test section setup. These are some of the results that we've obtained for the frictional factor. That is one thing we'd like to characterize as a function of Reynolds number. And I think the next slide will show some results on the heat transfer. Again, this is a friction factor result. These are overall heat transfer coefficients across the heat exchanger, because that's what we're really interested in. And you can see there is a slight change in it. As the Reynolds number increases, you will have an increase in that value by about 30 to 40% between the low value and the high value. So that was the first step that we started doing to characterize the type of heat exchanger before moving to a really more realistic prototype with high temperatures in it. Again, some of these results are shown here. One of the fluids that we have used, we've used air instead of the helium, and we've used a 5C silicone oil that we found will have similar characteristics for the FLENIAC, so that we can match some of the dynamic similitude, non-dimensional numbers that we are seeking. Now we make a jump and say something about the energy conservation side of things. And there are, of course, this is by no means exhaustive or anything like that. These are some of the things that I have worked on and have been used in the US in the applications for residential use. Basically, one of them is a popular thing called the radiant barrier system, which basically uses a highly reflective foil on both sides that is draped under the rafters, as they are called, under the roof. And the idea from them is to use their shininess or their low emissivity to try to reflect back some of the heat that comes in. And it does work well and reduces the roof cooling load by about 70 to 80%. Other benefits for this that we did not think about initially was also, since the duct systems are inside the attic installation, it also reduces the heat pickup by the supply ducts as they go through the attic to distribute the supply air to the different locations. And so we found that this could be even a greater benefit than the reduction of heat coming through the roof itself, actually. We've published a few papers on that as well. These products are available now on the market and can be used. Again, I don't think they would be very applicable in Lebanon because the construction of walls are different and there are no attics usually to use, especially in residential construction, unless you like to do something maybe up in the mountains where you have an attic and the space underneath it. But in the States, that's basically the way they build most of the homes at this point. Another application that I'm sure is being used here, probably for large installation, is a thermal recovery wheel. This is a very simple idea, basically, of using this flywheel, as it is called, to exchange heat between the outside air that is being brought into a building to provide the thermal comfort and provide some freshness into the building, and the exhausted air, as you can see, that is being exhausted to the outside. And this usually in installations like Las Vegas can cut a significant amount of energy from the usage of it because It can drop the temperature. I don't know if there are any temperatures here, but it can drop the required energy that you need to cool the outside air. Otherwise, if you did not have this, by about 50%. Now, you may say, what's the big deal about that? But if you have several tens of thousands of outside air CFM that you're bringing into the building, you can start appreciating the savings that this would reduce for you. So this is, again, designed for energy conservation mainly. Again, the use of, and I don't know if there is a lot of it here, the use of special sectioned walls that are a combination of concrete and high density foam. And these concrete walls, although they may have the same R value as a typical wall, we found from the Las Vegas applications, they do have higher thermal inertia in them, and due to that higher thermal inertia, they will retard the inlet of or the heat movement from outside to inside, and hence may have the potential of reducing the peak loading on a certain residence or building for that matter. And they have been starting to look at that in earnest and using those kinds of walls. Now, I don't know what exactly we do here. When I was working in the air conditioning area, it used to be the block wall, and they would cement it from both sides, and that's about it for Beirut, at least. I don't know, maybe in the mountains they used to have two walls with an air gap, but maybe there are experts here that can tell me what is being done, because in Las Vegas, basically, if you have a stick frame construction, as they call it, you have 2x4 pieces of wood lumber at 16-inch centers. You have thermal insulation between them, and then you have basically what is called it's a spray of cement, basically about 3/4 of an inch thick, to give some hardness to the whole wall, and that's about it. The drywall sits on the inside, so for a 4-inch installation, you're talking probably about an R13 for that wall. As I said, these kinds of walls do not have relatively higher R value, but the way they perform is because of their high thermal inertia for a system. So they do become effective in shaving off the peak loading in there. And these are just some cross sections that you see about how you may put an insulation in the middle of the wall versus this, which is called the stick frame insulation, which has basically fiberglass batt insulation and the drywall on the inside and the stucco, as they call it, on the outside. These are some results that we obtained due to measured values from 3 houses that we had the luck of doing some monitoring for a whole summer, actually, and you could see the design cooling load for some of these homes. The B is the cement home. The A and C are the difference basically is about 20% here for 3, let's call it summer months, August, September, and October. And that kind of proves our point, is that there could be a major reduction, and the difference in there is significant. So the cost, of course, is a slightly higher cost than doing the stucco frame, but I would imagine with the use of this in a more large applications, the cost would come down, as normally is the case with all these applications. The scale basically is very important in reducing those. This is basically a typical, again, FREUS unit called using an evaporative cooled system. So you have sprays that are spraying on the condenser coils, and the unit basically shows SEER ratings that are way above your typical units that are in use. For example, in Las Vegas now, the Energy Code recommends that we use a SEER rating of 13 or above. This one has at least 18 to 20 by the use of this mechanism. And they are a little bit more expensive, of course, than regular, the same tonnage unit, but over the lifetime of that unit, I think there will be some good savings seen from there. So this is basically what is provided from the manufacturer, and the red line is the variable SEER rating that you see for the unit as a function of the outdoor temperature, which does decrease a little bit, but nothing like the other units here, which you can see are more steep as outside air increases in there. I mentioned also that lighting is a very important method and should be looked at as far as potentially reducing the energy. We do have, of course, as you all have probably in this building, the fluorescent lighting, but there are new generations of lighting coming up. One of them is the LED lighting, which basically, one of the things that people like about LED is basically it provides you with a spectrum of light waves that are closer to natural light than fluorescent lighting. Also, its lifetime is fairly long, and it doesn't have the problems that fluorescent lighting may have, which is if you break the fluorescent light, there could be a little problem with mercury that comes out from these bulbs. So again, a lot of it is being studied. This is something I pulled from DOE, one of their reports, and you can see basically the prediction for LED lighting is going to pick up in the next few years. Again, everything, as I mentioned in my abstract, is dependent on cost, as you all know. So this is going to be an important one. Some other applications that can reduce your energy consumption is using solar energy for heating and cooling. And I'm not just saying domestic hot water. This is, we all know, of course, that's a long time ago. We're talking about coupling the collectors, the solar collectors basically here. These are the parabolic collectors. We're trying to couple them in some cases for absorption chillers and using those basically as our driving force for HVAC. Now, there is a lot of work still there. The cost is still high, as you can imagine, but this is one of the things that people are looking at to try to couple solar energy with HVAC installations. And I just thought I'd put this on the board to show you a typical type of installation. Geothermal, again, is probably very familiar by now. This is basically where you reject the heat of the condenser from an HVAC unit to the ground. And the idea from doing that is to reduce the condensing temperature. And usually you get some good improvement in the SEER rating of these units. You have to dig a shaft, obviously, in the ground, and you have to pad it with certain material that would increase the thermal conductivity from those pipes. But it does work well in both cases as a heat pump for cooling as well as heating. And a lot of the units also come with an economizer that can recover some of the heat and use it to preheat domestic hot water as well. So the unit, of course, is more expensive on a ton-by-ton basis than a similar unit that does, of course, air conditioning only. But in some cases have been applied in the US. They even use them in Las Vegas, which is the ground is fairly dry, but when you put those materials in the loops, it does improve the thermal conductivity, and they have found some reasonable savings for these. You have basically a water loop that is activated by a pump, and this basically rejects the heat from the condenser to the ground. Of course, you have to keep the loops at a certain distance from each other, usually about 10 to 15 feet, because if you put them too close, then you'll have short-circuiting between the different loops themselves, and you can get a good system. They've used those in a lot of the high schools and elementary schools in the US because they tend to have a playground outside the school which can be dug up before you install the grass and all that, and you put those loops and then close it up. So it does make for a good application. And of course then the grass gets watered to keep it alive, so that improves even the heat transfer better from all these loops in the ground. So this is We've done some work, again, on duct leakage. As I mentioned to you, in residential applications, we do use a lot of ducting in the States still. Trying to determine where the leaks are and trying to plug them can be a very important one. It's not rocket science, but it's a very important activity and can save over the total number of residences in the state a lot of dollars and a lot of energy, obviously, from the consumption of the of the U.S. So we've done some work on trying to determine how we can find the leaks locally as opposed to doing it on a broad basis. There are tests from ASHRAE that give you those, but they really don't test the ducts at the operating conditions of the ducts. So their values that you come up with are only can be compared by comparison to other duct leakage tests. So you can say this house leaks more than that house, but it doesn't really tell you exactly what is the leakage at the operating conditions. So we were trying to improve on that and see what kind of methods we can use to plug up those leakages, because that's obviously the most important thing after you find the leaks. As a conclusion to the general talk, and again, some of these may be or may not be applicable to the area here in Lebanon, we have several energy generating conservation technologies exist to help reduce the carbon footprint of modern power applications. And again, this is a very small survey of what's out there. By no means this is exhaustive. The technologies are in different phases of development and implementation. As I've shown you, some of them are still in the lab stage. Some of them have gone out, and we're looking at full prototypes to be applied. A very important key is number 3, which again, I don't know how we are doing it in Lebanon, or if there is an effort in Lebanon to do that. We have in the States, financial incentives are still needed to entice potential customers to adopt these technologies. Payback periods are still significant for smaller installations. What I mean by this is in the US, certain technologies, not everything, the federal government or the local governments in Las Vegas, for example, or the, as they call it, the Clark County, they come to you, they say, okay, if you install PVs, we will give you $2 or $3 per kilowatt installed or per watt installed, and they will give you some tax breaks as well, the federal government that is. So they will encourage you to shave off the initial installation cost of these technologies. And of course, it doesn't need a rocket scientist to figure out that you're going to be accruing some savings from the reduced usage of electricity, because the way they install these systems is they put a watt meter that would read in reverse. In other words, everything that you generate and you put back on the grid, there is no storage here, is recorded, and basically the power company will give you credit for everything you have generated and put back on the grid. So basically what you're paying is any difference between what you consumed from the grid and what you put back in the grid. So in a lot of cases, if the system is designed and selected properly, instead of paying, let's say, I'm just throwing a number just to give you an order of magnitude feel, instead of $250 a month, you could be running at $30 or $40 or $50 a month. Now, of course, you have to work it from the payback, and you have to figure out what the increase in kilowatt hour is going to be over the next few years, but it will always come up with a reasonably good figure. So the incentives, the financial incentives are very important to make these budding technologies take hold and have people consider doing that. And again, I put the question to you, is there anything like that, or does I know the university is obviously going to be the prime mover in this with some of the engineering professional societies, but I don't know if the government, the local government, does anything to encourage usage of these kinds of energy conservation technologies. Is there anything like that? Does anybody know?
We are still interested in power, political power, not
Well, I don't have any prescription for political power. I can generate KWs, but not political power. So I take it that there are no incentives or any initiatives by the government. There are initiatives.
Supported projects, the energy planning center at the Ministry of Energy and Water. There are lots of initiatives going on, but even in AUB, we have a specific program that has been developed to educate professionals to practice,
I've read about this on the web, but what I meant is, are there any financial incentives that are offered by local governments or?
Not yet, but they're getting lots of donations, for.
Great, yeah, I mean, it takes.
In Cyprus and
yes.
Greece, there is incentive to put solar heaters for at least water on the roofs.
Yeah, I mean, now water, I mean, you don't even need an incentive. It pays for itself in probably 2-3 years. What we're talking is about these more exotic applications such as PVs and things like that. Their cost is still high, but a lot of people are doing that partly because they like to sort of help the environment. The other part is they do get these incentives from the federal government. And they started out with almost $5 to the watt, to the installed watt initially. Now it's coming down as more people are more interested. There is this mass, I think the cost of PVs are coming down as well. Everybody is looking for China to come up with the next new, whatever, silicon wafer or whatever it is, to drop it more, maybe by an order of magnitude. Then it may stand on its own and doesn't need those rebates from the federal government. So
I know my brother wants to put solar to generate electricity on the roof, but he found out it's too expensive. So
by itself, definitely it is prohibitive. I can tell you that. Yeah, you have to be given those tax incentives, and you have to be given the fact that you can sell, quote unquote, the KW hours that you generate back to the utility. And that's what you need, this reverse watt meter that will record how much you have.
You have this in Las Vegas?
Oh, yeah. Oh, yeah. They put 2 meters for you side by side, and everything is done electronically. So you get basically a bill at the end of the month. You've given us that much, we've used that much, and the difference is what you get charged for. Yeah. These are my own wish lists, so I personally feel that Lebanon should move to perform some limited field studies on some of the more mature technologies, such as wind. Wind technology is probably one of the more promising one. The reason I'm saying that, in the areas where it is applicable, the cost of wind energy per kW is about, and this is a rough number, about $1,000 per kW installed. This is much better still. It's in the ballpark of a fossil fuel plant, as opposed to a PV, which is way above that, maybe in the order of 2,000 to 2,500, 3,000, depending on what kind of PV system you use. So it does have promise, and I do encourage anybody who is doing those kinds of data collection studies in all the areas of Lebanon to quantify their potential and would go ahead with it, because at this point that's probably the most feasible thing to do. My other conclusions are the power technologies in order of market penetration, and again this is my own personal, is wind power where applicable, thermal solar is the next probably, and then the last one is I put is solar electric PVs, unless, like I said, there is a major penetration or a new discovery in PV physics that would bring those costs down. For energy conserving ones, again, I feel that for the direct applications, and again, depending on the construction, radiant barriers and reflective paints, which do basically the same thing, they reflect a major amount of heat that comes from the sun on the structure, are probably at this point some of the promising ones. The next ones are insulating walls, low energy lighting. This is still in the research. We hope to try to engage the public electric utility to offer some rebates for these energy generating / saving ones in reducing the demand on its generating power plant. And again, this is my wish list. And just to leave you with a couple of impressions from Las Vegas, this is a photo I've taken of a mountain that is close by, about an hour drive from Las Vegas. It's the peak, as you see, is about 12,000 feet high, 3,600 meters. It's called Mount Charleston. It has 3 ski lifts, and they run from November till April. So it's not only desert that we have around Las Vegas. And the last thing that some of you may have heard is the new development we have in Las Vegas, which is the city center, which the Dubai International is a partner of. They've put 50% of the money in, about $5 billion, and they just finished this, I think, in the Christmas holiday of just this past year. And it's probably I think it's considered one of the largest construction projects of residential construction in the US so far. And I don't know. Residential in the sense that there is a casino, there are several condo units, high quality condo units. Hopefully, a lot of them are green rated, green buildings rated, and so on and so forth. So, that's why they went bankrupt. Well, I don't know. Dubai International was trying to pull out, and then I don't know. They seemed to decide on against that eventually. So maybe Abu Dhabi helped them out eventually. But the building is almost finished. I think they've commissioned everything, and I'll be more than happy to answer any questions that you may have. And that's it. Thank you for your attention.